Hello and welcome to this free preview lecture series of my on-demand FE Electrical and Computer Exam Preparation course. In this lecture, we are going to discuss diodes, which are a very important concept within electronics section of FE Electrical and Computer Exam specification. If you learn how to solve diode circuits, solving the BJT circuits, op-amp circuits, and MOSFETs will become a lot easier for you. Before we dive into the content, I would really appreciate if you could like this video and click the bell icon and the subscribe button if you haven't already done so. Hello and welcome to our multi-part lecture series on the topic of diodes, which is a subsection of electronics. In this lecture, we will introduce what a diode is. We will review its forward biasing and reverse biasing. We'll discuss ideal diode and compare it with non-ideal diode. We will look at two commonly used models of non-ideal diodes. The first one is exponential model, which is based on Shockley equation. And the second one is constant voltage drop model, which is primarily used for diode circuit analysis, and that's why it's important. And at the end, we will look at diode circuit analysis using ideal diode model and the constant voltage drop model. Diodes. Diode is a semiconductor device that conducts current in one direction only, which is a very important property because it helps us making use of it as an electronic switch. It has two terminals. The positive terminal is called the anode, and it is basically the p-type region and represented by the triangle. And the negative terminal is the cathode, which is the n-type region, and it is represented by a dash or a bar. At the end of the day, a diode is simply a p-n junction. Okay, so P and N, and we have explored p-n junction in quite a bit of detail as part of our review of semiconductor basics. Okay, so this p-n junction is basically translated into anode and cathode. Okay, so this is P and this is N. Now, when it comes to biasing of a diode, it's no different than the biasing that we discussed for the p-n junction. So in a forward biased mode, we have positive voltage applied at the anode and negative voltage applied at the cathode. So anode is connected to battery's positive terminal and cathode is connected to the negative terminal. And the diode will basically act as a closed switch or a short. Okay, so when we have positive biasing, this basically acts as a short wire. In the reverse bias mode, anode is connected to battery's negative terminal and cathode is connected to the battery's positive terminal. So this is reverse biasing. And in this case, we have negative voltage, which is being applied. Okay, so the current won't be allowed to pass through because it will act as a open circuit. Okay, and it is basically acting as an open switch. So this is a key property because now we have an electronic switch which can be closed or opened depending on the voltage that is applied across it. Okay, so this means that no more mechanical switches, and essentially this was a great leap forward in the world of electronics with electronic switching, and then we will discuss later in this section transistors, which helped us in amplification. So electronic switching and amplification basically revolutionized the modern electronics. Let us now take a look at an ideal diode now. So when we have the diode in the forward bias mode, when the positive voltage is applied across it, then it will start conducting current. Okay, so we just have to apply some voltage slightly greater than 0 volts. And really, for an ideal diode, the junction potential is equal to 0 volts, right? So as long as the voltage is 0 volts or higher, then the diode will start conducting current. And you can see that it's conducting infinite amount of current because the assumption is that there's no internal resistance which is offered by the diode. So this is literally a short wire. Okay, and as soon as you apply a negative voltage across the diode, then it becomes gets into the reverse bias mode, and in the reverse bias mode it is an open circuit. So when the voltage is negative, then current is 0. When the voltage is equal to 0 or slightly higher than 0, then the current is positive and it will act as a short and it can conduct infinite amount of current theoretically, right? So this is an ideal diode. But as we know that nothing is ideal, diode has its own characteristics. Practical diodes are non-ideal, and we will discuss two very basic models of non-ideal diodes. The first one is the exponential model. According to this model, the current in a diode is dependent on various factors, and it basically increases exponentially as you basically go past 0.7 volts. Now 0.7 volts, I pointed out, this is basically the junction potential. This is the potential, the voltage that exists across the PN junction when the depletion region is formed. Okay, so I explained to you that there's an electric field that is set up and you have positive charges here, negative charges here. So it's like a mini battery and it has 0.7 volts. When the applied voltage is higher than 0.7 volts, then the current will start flowing. Okay, and the current doesn't really flow until you are greater than 0.7 volts. Okay, the applied voltage in the forward biasing mode is greater than 0.7 volts. And according to Shockley's equation, which is very important, it was a major breakthrough, it basically explains us how this current will increase with the increase in voltage. So VD is the voltage that is applied across the diode in the forward biasing. VT is the thermal voltage, which I explained to you is 0.0026 volts if we are at room temperature at T is equal to 300 Kelvin. Okay, and this emission coefficient, okay, so this looks like a Greek letter N. It is also used typically for efficiency. It is generally equal to 1 for silicon, and its value is typically between 1 and 2 depending on the type of semiconductor you are using. Okay, and IS is the saturation current. Okay, so IS is the saturation current and K is the Boltzmann constant. So I forgot to give you this value of Boltzmann constant in the previous lecture, but this is the value of Boltzmann constant, and Q is equal to 1.602 by 10 raised to the power minus 19, which is the charge on the electron of the electron. We also have another model for non-ideal diodes, which is called the constant voltage drop model, and it is typically used as part of diode circuit analysis. So in this case, we basically say that, okay, we have an ideal diode, okay, and this ideal diode actually doesn't have 0 volts of voltage drop across the PN junction. It has 0.7 volts of voltage drop. So rather than having a curve like this, okay, where as soon as you hit 0 volt, you can start conducting infinite amount of current, we actually look at this graph like this. So you have to go past 0.7 volts or reach 0.7 volts. After that, you can basically start conducting infinite amount of current. Okay, so the only difference is that when you are analyzing the circuits, rather than using 0 volts, you have to use 0.7 volts. And this is called the non-ideal constant voltage drop model of the diode. And we will go through a bunch of examples now in order to make use of this non-ideal constant voltage drop method to analyze diode circuits. So let's start with this example. Example number 1, it is asking us to calculate the current which is passing through the given circuit using ideal diode model. Okay, so as soon as you see the word ideal diode model, it basically means that the voltage drop across the diode is equal to 0 volts. Now the current passing through this circuit can be given as 4 volts minus VD divided by 2 kilo ohm, right? Because I can actually convert this circuit into a 4 volt battery, which is already provided to us, right? And a battery which is representing the voltage drop across the diode. So remember, this is the positive terminal and this is the negative terminal. Okay, so this is positive, negative, and the series 2 kilo ohm resistor, right? So from a resistor standpoint, these two voltages are actually opposing each other, right? Because if these batteries were connected like this, then we would have 4 volt plus VD type of situation, right? Because if it's positive, negative, then the batteries add up. But if it is positive negative and over here it's positive negative, then they basically oppose, because this battery would be trying to pump current in this direction and this would be trying to pump in this direction. Okay, so that's why the current passing through is basically through the circuit is basically 4 volts minus VD, which is the total voltage. Okay, we simply take these two into consideration, divided by 2 kilo ohm. Now we are given an ideal diode model. So VD is 0 when the diode is forward biased, and it's pretty clear that this given diode is forward biased because we have a huge positive voltage being applied on the triangle portion, which is the positive, the p-type region. Okay, so that basically means that we have this particular diode in forward bias, and ID is equal to 4 volts minus 0 divided by 2 kilo ohm, which is equal to 2 milliamps. Now example number 2, we are being asked to calculate the current passing through the given diode circuit using ideal diode model. And you would notice that in this case, the direction of the diode has been flipped. Now this flip in the direction of diode has huge implications, because all of a sudden your positive terminal of the battery is now connected to the bar, okay, which is the N-type region, okay, and that basically means that this diode is now in a reverse bias mode. And if the diode is operating in the reverse bias mode, then you actually don't even need to go through this calculation, because it will act as an open circuit, and the diode current and the current that flows through this circuit, which is the same as the diode current, will be equal to 0. Now example number 3, we are being asked to find the current passing through the circuit using the non-ideal CVD model. CVD is a constant voltage drop model, and we are told that the voltage drop across the diode, if any, would be 0.7 volts. So the entire setup remains the same. The only difference is that, okay, we first have to verify that what is the mode of operation of this diode. It is very clear that the positive terminal is being applied at the p-type region. Okay, so this means that the diode is in forward bias, and instead of using 0 volts over here, we will actually use 0.7 volts. Now the current through the diode with the CVD model is equal to 1.65 milliamps. Example number 4, we are being asked to calculate the current passing through this circuit using non-ideal CVD model, and in this case I have 2 diodes in series. So what happens when we have 2 diodes in series? When we have 2 diodes in series and they're forward biased, basically their voltage drops will add up, because now you have this small battery of 0.7 volt and this small battery of 0.7 volt. So the overall battery, because the external voltage is quite big, so the overall battery will simply be 4 volts minus 0.7 plus 0.7 volts. Okay, and you will just substitute that in this equation and you'll find that the diode current is even lower now. It is 1.3 milliamps. Let us now take a look at a much more complicated circuit involving 2 diodes, and this problem is from the study guide. We are being asked to find the operating states of these diodes D1 and D2, and this is a circuit that we will make use of. And the other important piece of information is that we can assume ideal model of the diodes. So whenever we are provided this type of a situation involving multiple diodes, we always start with an assumption. So let's assume that both diodes are on, and generally speaking, it is a good assumption to start with. Okay, unless you can tell from the circuit right away that because of the biasing, that won't work out. Let's say if I had a battery over here which was -6 volts. Okay, so the negative terminal was connected to the triangle. It would clearly tell me that, okay, this diode, really the chance of it being operating in the forward bias mode is very, very low, unless this terminal has even lower voltage, so that the voltage drop across the diode is still greater than 0.7 volts. Okay, so let's assume that both diodes are operating in the forward bias condition. It means that both diodes are shorted. Okay, now we have to calculate the current that would be passing through each of these diodes in order to verify whether this condition is true or not. So you can see that ID1 will simply be equal to 5 volts minus 1 divided by 1 kilo ohm. And how do we calculate that? We have this 1 volt battery, which basically means that over here we have 1 volt. So the current passing through this resistor, which would have passed through the diode as well, is equal to 5 volt minus 1 volt divided by this resistor. So this is 3 milliamps, which is good. And we also know that ID1 plus ID2, so ID1 plus ID2, so these are the two currents that are entering in this region, right, at this node. So this should be equal to the current which is passing through the 2 kilo ohm resistor. And the current that passes through the 2 kilo ohm resistor is equal to the voltage across this 2 kilo ohm resistor divided by this resistance. So we know that the voltage across this 2 kilo ohm resistor is 1 volt. So 1 volt divided by 2 kilo ohm is equal to 0.5 milliamps, okay, which means that ID2 is simply equal to 0.5 milliamps minus ID1, which is 0.5 minus 3 milliamp is equal to minus 2.5 milliamps. So ID2 is negative, and this result is not consistent with the assumption, because when the diodes are on, the current through the diode is actually positive, which is true for ID1, but we just saw that for ID2, based on these assumptions, the current is negative, so it's not consistent. So we can no longer assume that both diodes are on, so we have to use a different assumption now. So let us now assume that both diodes are not on, but only D1 is on, so which again is a safe assumption, because we sort of confirmed that for this setup D1 was on. It was D2 that we were having issue with, so we will switch D2 off. Now if D2 is off and D1 is on, it basically means that D1 is still a short wire, but D2 is basically an open circuit. And you have to make note of these polarities as well. So the triangle always represents positive and the bar represents negative. So notice that for VD2 I have maintained this positive and negative, and it's important to understand that. So ID1 again is equal to 5 volt divided by 3 kilo ohm. Well, not again, because now we are looking at the current that is passing through this ID1, because this is open circuit. So it's simply, the ID1 circuit is simply 5 volts, right? And a series resistor of 1 kilo ohm and a series resistor of 2 kilo ohm. Okay, so 5 volts, and the current passing through the 1 kilo ohm resistor is actually equal to ID1. So this simply becomes 5 volts divided by 3 kilo ohm, which is 1.66 milliamps. So far so good, because this is greater than 0. And the voltage across the second diode is very important to understand, because you see that the positive terminal has 1 volt, which is good. So the voltage across diode 2 becomes 1 volt minus this voltage drop, okay, the voltage drop across the 2 kilo ohm resistor, because VD2 is equal to VD2 at the positive terminal minus VD2 at the negative terminal. So for the positive terminal, we already established that this is 1 volt, and for the negative terminal, it is the voltage drop across the 2 kilo ohm resistor. So the voltage drop across the 2 kilo ohm resistor is simply equal to 1.66 milliamps, which was this current, okay, the diode current, times 2 kilo ohm, and that is roughly 3.2 milliamps, 3.2 volts. Okay, so we have roughly 3.2 volts, and 1 volt minus 3.2 volts is roughly 2.3 volts, which you can see is negative. Okay, so because the voltage across the diode is negative, it basically means that this diode indeed is off. Okay, so we verified our assumption. So D1 is on and D2 is off, and the current passing through D1 is equal to 1.66 milliamps, and the voltage across D2 is negative 2.33 volts. Now, if for some reason this voltage turned out to be positive, then we would have to make use of another set of assumptions. Okay, so this is how you would solve the diode circuits iteratively. Okay. And the other curveball that can be thrown in these type of circuits is that you might be given a non-ideal diode model with a 0.5 or 0.7 voltage drop. And the difference it would make is that now you would have to consider these voltage drops into, take these voltage drops into account as well. In this section, we introduced diodes. We looked at their forward biasing and reverse biasing. A junction diode is simply a PN junction. We reviewed ideal diode and the non-ideal diode. So there's a constant voltage drop model and there's an exponential model which is underlined by Shockley's equation. And then we did a few practice problems involving diode circuit analysis. If you found this preview lecture helpful, I am confident that you will also greatly benefit from the full course that contains over 150 lectures and covers all the topics that are found in the latest NCS FE Electrical and Computer Exam specification. You will also get access to tons of quizzes and mini exams in this course that will help you get additional practice, along with a bonus full-length computer simulated practice exam. This streamlined and well-reviewed course comes with an amazing 30-day full refund policy, no questions asked. On top of all this, I have also included a special discount link in the text section of this video.